beneficent. This is our second lecture in track 1, and which will be primarily designed for applied mathematics. Let us first recall what we discussed in previous week. In our first lecture, we discussed that what is going to be the course scheme that we are going to discuss in this course. And secondly, we discussed some types of MCQs that we might expect in these type of competitive exams. And then we directly move towards multivariate calculus, in which we discuss what is dot product, what is cross product, and what is the equation of line in 3D, and what is the equation of a plane in 3D. So our main goal is to take single variable calculus and extend it to the case of multivariate calculus in 3D. So whatever topic we are going to discuss, we will be discussing that thing first in single variable, but not in detail, but then we will extend it towards multivariate case. So we have so many topics to be discussed in this multivariate course today, but I will be as precise and concise as possible so that within short span of time we may discuss more and more topics. So our today's first topic is going to start from 3D curves and their tangents. So the first thing is that, leaving 3D, what do we mean by a curve that lies in 2D? Because a curve is basically a one-dimensional shape. And when you take a circle, you might be teaching to your students that a circle is a 2D shape. So circle is basically a 1D shape that lies in a two-dimensional plane. So circle is 1D shape, but basically it lies in a plane. That's why sometimes we may call it a 2D shape. So we show students, whenever we are discussing, we show students some sort of circular disc. So that circular disc is a 2D shape, but circle itself is a 1D shape.
Curve पर नौ
जी जी
वे 1D time पर lie लेकिन वे time पर coordinates दोसे 2 dimension lie
yes.
So space curve जो की होगी आहे माइंड में नंबर वन वो सर अगर space को वाज जो तू आज जा सब points के एक plane पे ना हो जाए वो 3D में lie कहीं
yes. So we make one-dimensional shape, but that curve lies in either 2D or 3D. Because whenever you see a 2D plane, like the example is XY plane, we take a circle. So we know very well that this is a 2D shape as we teach to our kids, but basically it's a one-dimensional shape that lies in two-dimensional plane. So what we show to the students, that's basically a disc. So when we teach circle, we show students some sort of circular shapes, and that is a circular disc. We may call it a 2D shape, but circle itself is 1D. Because what you can do, you have a circle, you can take any piece of circle, let's say this piece, let's call this point A and this point B. What you can do, you can map this particular curve on a single line R. That's why we call this to be one-dimensional shape, or we call it one manifold or one-dimensional manifold.
यानी वो length
Yes.
से area वाली मार चुका
Yes, that's the same thing. So we have this particular curve that lies in 2D. I am asking what should be the equation of this one. We have a general equation of circle, we know very well. We have a standard form as well. But I am going to take one particular form. Let's
origin.
Yes. The center is at the origin and the radius of circle is R. Then the equation is x square plus y square equals R square. But the question is whether it is a function or not.
अधिक क्यों सब फीचर है सही होता है
Yes. Because when we see
Vertical line.
Yes.
Vertical line.
we apply vertical line test,
सही है
so it cuts this particular curve at 2 points, hence it is not a function. So we are interested in to convert this particular shape into some other sort of functions, and we make all those functions to be functions, because this is an equation but this is not a function. So we try to rewrite this particular thing in such a way that every component itself is going to be a function, every component. So what we do basically, we parameterize this particular thing. And we know very well, this each and every point on this particular circle can be represented by the x component of this one is, I think,
R
cos t or r cos theta, and the y component is r sin t. So this each and every point, and we know very well the distance from origin to this particular point is r, so this r remains same, and when we move along this circle, then we get all these values cos t and sin t. So we can get each and every point on this circle just by changing these two particular points. So we call this to be the parameterization of this circle, where t is the parameter and r is a constant which shows the radius of a circle. Now the question is, why do we do that? If we see this particular thing, x is equal to r cos t and y is equal to r sin t, when we look at this function independently, this equation independently, is it a function?
Yes, sir.
We know very well that in this one, independent variable is t, dependent variable is x, and cos t is a function, because we know very well the graph of cos t. So what we do, we just divide this function into two different cases, and these two cases independently are functions. What is the benefit? Then we can apply all the properties of functions over here. Okay, how can we define continuity here? How can we define differentiability here? And how can we define integrability or something like this on these particular components independently? If we are taking this particular thing, then we might be stuck that if this is not a function, then how can we define continuity on that? How can we define limit on that? How can we define differentiability on that? We can define in some other sense, but it will not be something that we can apply a single variable calculus case to extend it. So it would be somehow difficult. There might be so many other reasons behind this parameterization, but this is one of the reasons. Some people are doing some sort of rational parameterizations of circle. This is a parameterization of circle, because what you can see that whether this is something right or wrong, just put the value of x to be r cos t and y to be r sin t, then this will satisfy this particular equation. I think there is another parameterization for a circle. I don't know exactly, but I am just going to recall. The x component is given by 2t divided by 1 plus t square, and y component is given by 1 minus t square divided by 1 plus t square. And since the radius of the circle is r, so I am going to just multiply both components with r. Now just I ask you, when you put these particular things in this, whether you get r square or not. So, okay, if you get this, so do you say this is a right parameterization of circle? So the answer is yes, because these two components independently, when satisfy that equation, we call this to be the parameterization of the circle, and depending upon parameter t. But what is the difference between this one and this one? This will give us a value which is a real number. It means this can give us a value which is rational as well as irrational. But this always gives us a value which is a rational number, because t itself is something like an integer or rational number. When you put it there, you will get something that is a rational number. So here people claim, there are some people that each and every point on this circle can be represented by these pairs of rational numbers, then why is their use of real numbers? There are some people who question the existence of real numbers, that okay, the real numbers are problematic, and they give introduction to a new type of trigonometry, what is called rational trigonometry. There is a book on that as well. So this is another thing. We can study these particular parameterizations when we are studying either vector calculus or differential geometry.
सर
जी
जी ये अपना पैरामीटराइजेशंस कई से है ना सर्किल दी होने
Independently, and this function independently. Then you claim that these independently are functions. But when you combine these in this type of thing or that type of thing, according to single variable calculus, it is not a function. But what you can do, you can apply different properties when you study these things. We are coming to that right now. What do you mean by a 3D curve? The curve that lies in 3D simply. This can also be the curve, but we are going to draw the same thing in 3D. So, this is simply, let's say this is R3, and this is our circle which lies in XY plane. What is going to be the parameterization for this one? The parameterization is going to be same R cos t, R sin t, but we are claiming the z component to be
0. It's like 2D movie.
Yes, the same thing is there, but the z component is 0. It means when we apply t here, we are not moving in z. Our z is fixed at 0, but I want to draw a circle. Here the value of z is 0, here the value of z is, let's say, 4. I want to draw a circle here, so I will be changing this particular coordinate to 4. That would again be a circle, but it would be translated 4 units to the upward direction. But if I do this particular thing, r cos t, r sin t, and let's denote this by a vector. My third component is t. It means whenever I change the value of t or I increase the value of t, then z component also increases. So what does this represent?
ये वेक्टर हो तो 2D में हो तो ना t को वो तो वैल्यू हो तो जो हाइट है वो
Yes, you can say it.
कोई इंटीजर हो.
Yes, this can be a point as well as a vector. If you are considering it a vector, then it would be a position vector. If you are considering it a point, that would be just a point in 3D.
Tuple.
Yes.
Triple order.
Yes, yes. So, what is this? What type of curve is this?
This shows the point of space.
Yes, point of space.
हेलिक्स हेलिक्स का था ना.
Yes, helix or helix.
Helix कैसे? The helix equation.
So, when you put t is equal to 0, then what happens? This is going to be 0. This is going to be 0.
This is the R.
But the value of x is going to be
1, then R.
cos 0 is 1, this is going to be r. If you are taking this to be x, then that point would be here. If you are taking this to be x, then that point starts from here. Let's take anywhere. Then what happens? This will give us a circle, but when you increase the value of t, the circle will be increased in the direction of z-axis as well. So, simply it would be a circle, but it will keep increasing in the direction of z. Or simply what you get a spring type structure, and what we call it? We call it helix. This is one of the most common example of a curve in 3D. What happens? Its z component is also there, and it contains t, which is a variable. If it is a variable, it means we are also moving in the direction of z. So this is what we call a 3D curve. So let us take a generalized example for this. So a 3D curve is basically a position vector r of t, and it depends upon parameter t, which is f of t I hat plus g of t j hat plus h of t k hat. So we call this a curve in 3D, and if you compare this particular thing with that surface that we have, so f of t is or cos t, g of t is or sin t, and h of t is just t. Now you can define the limit as well as derivative in the simple case as we have. So you want to find out the limit as t goes to 0. So when you have a function, then you can apply limits, then you can apply continuity. That's why these f, g and h independently work like a single variable function. That's why it is good to do this thing. So this is what we call a 3D curve. Now the next idea is, we are not going in depth to this particular thing, but we'll be in need of one or two ideas based on this. That's why we are discussing. Now the thing is, we have a curve that lies in 3D. How can we define the tangent of this curve? What is tangent?
Tangent
Or the what we call the slope of a tangent line. We call the derivative at that particular point. So what do you do here? You just differentiate with respect to t, and you just put the value of t, and you will get the tangent to that particular space curve that lies in 3D. So tangent is defined as just the derivative of this particular r of t with respect to t. And how you do that? You know very well how to differentiate a single variable function. So there is nothing new. We are just going to extend the idea of generalizing it. So it is going to be df by dt. I simply write it as prime of t I hat plus g prime of t j hat plus h prime of t k hat. And if you specify any particular point, then you will put the value of t to be t naught, and just you put here t is equal to t naught, and whatever that point can be. So this is the main thing that why we are going to study the parameterization of these curves. And sometimes what we need the unit tangent. And what do we mean by that? The tangent,
Which length is 1?
yes, the length of tangent vector is going to be 1. This will be a vector, so it is better to represent this particular thing with t and an arrow. So when you want to normalize it, a normalization of a vector means just take the vector and divide it by its length or mod. So sometimes we'll be in need of that particular thing. So what is a tangent vector? If I have this particular curve or whatever a piece of curve I have, and I want to define the tangent at a particular point, that would be this arrow which shows the direction of the velocity of a vector. Direction of the velocity of a vector, or simply the velocity of a vector, because we know very well velocity is a vector quantity and t with an arrow is also a vector quantity. But when you find the absolute value or the length of this vector, we call that particular quantity to be speed. So what is the difference between velocity and speed? If you are talking in the sense of mathematical way, so the velocity is vector and speed is scalar. So in mathematics, velocity is going to be something in the vectorial form and speed is going to be a constant or a scalar. In the same way, we have a very basic question, I think. What is the difference between gradient and slope? We might have heard.
ग्रेडियंट जेको आहे उहो कंहिं बि स्केल पॉइंट फंक्शन जो जेको आहे उहो डेल सां हर x y z जे डेरिवेटिव जो सम आहे.
What is the basic difference?
बेसिक डिफरेंस सर ग्रेडियंट जेको आहे इहो कंहिं बि सरफेस ते हिकिड़ो टेंजेंट वेक्टर आहे.
Tangent vector.
नॉर्मल वेक्टर, सॉरी सर, नॉर्मल वेक्टर आहे हिकिड़ो सरफेस ते नॉर्मल वेक्टर.
Normal vector, but what is it? It's a vector.
It is a vector.
It's a vector.
स्लोप स्केलर होगा.
What is slope?
Scalar होगा.
It's a scalar.
That's a
It's scalar. So when we talk about gradient, it's a vector quantity.
yes.
When we talk about slope, it's going to be something scalar. But simply in 1D case, in single variable calculus, we don't have that difference mainly. That's why we are not differentiating between what is a gradient and what is a slope. But both are same. But the difference is one is a vector, another is a scalar quantity. Okay, now we know very well how can we define tangent to a particular 3D curve. Then what is going to be normal?
The rate of change of tangent.
So reciprocal and negative में.
Reciprocal negative, but what does it mean?
It is
We are not going to define it mathematically, but we must know.
It is a normal vector on the tangent.
Normal vector on the tangent.
Tangent point the normal vector.
Yes. So
Orthogonal.
yes,
Orthogonal perpendicular.
if this is a space curve and this is my tangent to it, a vector which is orthogonal to this one
Yes sir.
is called normal. But the thing is that what should be the direction of that orthogonality? Either this one
Inside no.
or this one.
Any path.
Which one?
Sir. Upward. Sir, positive side from the upward, negative side the down here.
Basically, it is always the direction in which the curve is changing. Always inside direction. So yes, this is going to be your tangent and this is going to be your normal. Always inside that particular curve.
साइन की गाल चढ़े नेगेटिव हो जाए तो वो भी
Negative?
अगर नेगेटिव हो जाए तो वो शायद मथे.
What is tangent? It's a vector.
असा नॉर्मल है साइन जी जो ना वो वाकई ये थी मौके का बटन. नेगेटिव हो जाए तो मथे थी सके बोला ना. वो भी इनसाइड.
पर सर भूकंप में ये लिखा है जरा भी नॉर्मल फाइंड करना है सर वो पॉजिटिव नेगेटिव भी नहीं पास कर रहे हैं माना तो हो भी आए पर जेड़ो ता चॉइस में
अक्सर इनसाइड होगा.
वधिक सर ता जी गाल
Yes.
तो माना भाई सर फाइंड क्या है माना पे नेसेसरी तो भाई फाइंड क्यों लिखे हुए हैं.
There might be two, but we want uniqueness. That's why
Yes.
it is better to take the inward direction.
Yes, पास करिए.
Yes.
वो सर बेहतर है जेन तरफ डायरेक्शन में.
Okay, so we are going to define what is tangent, what is normal, what is binormal, what are the equations that are satisfying these three things, and how can we connect these three things, but not in this course. Not in this course, not right now. Okay, the next idea is a bit interesting and a bit simple. How you find the length of curves? 3D in 3D.
सर लेंथ ऑफ कर्व.
Yes.
सर इंटीग्रेशन है सर ये सर.
But how?
कोई भी फंक्शन आसा वट d अल्फा by dt उन्हें मार लाई इंटीग्रेशन 0 to t तो उन्हें कर्व जी लेंथ मिल गई असांखे.
Come to a 2D case
2d
and give me example how to do it.
सर कोई भी फंक्शन खणो तो अल्फा ऑफ t that is equal to t square plus t.
No, we are coming to a 2D case for now. We are extending it to 3D, but we are discussing only a 2D case right now. For example, because we have to build the idea. There are lots of formulas in books, there are hundreds and thousands of formulas. We can memorize the formulas, and ultimately when the test comes, we are going to forget the things. So when we have a basic idea, then we can extend the things in a quick way, and even we can recall the things. So, you have a curve, whether it is 2D or 3D. What you want the length of this curve starting from a single point to another point. What is the basic idea in calculus, or what is the basic idea in integration? What you do basically, you divide this into different pieces. We call it the partition. You know very well. And what do? You approximate this with a straight line. Let me take a look. So you approximate this curve with a straight line here, straight line here, straight line here, and a straight line here. So this is the idea you can build anywhere, and then simply you never forget the things. Now you want the length of each of this straight line, and you just add these. That's going to be the length of the curve. This is the simple idea of integration of the calculus. Because the word calculus means to calculate. To calculate. And How you calculate? You calculate lengths, you calculate volumes, you calculate areas, and you build the basic structures on that. So let us name this particular length to be delta L, and I am going to represent it with some sort of index I, because then I will take the value of I to be 1, to be 2, to be 3, and so on. And how can you find this? If you live in 2D, you have a particular curve, you want this length, what you have delta xi, and you have delta yi. You want this delta li, you know very well delta li is going to be square root of delta xi square plus delta yi square. Are you okay with this? Using Pythagoras theorem.
सर मथी लाइन बनाए ना सर
No, we are finding this one.
ठीक सही है
Because we are going to approximate this curve with this straight line. And this approximation is a straight line and we can find in this way. So what would be this one?
सर pythagoras theorem में लगा दो सर
Delta xi square delta yi square plus delta zi square in square root. Is it okay?
This is same with the circle.
Yes, same thing. You have any curve, whether in 2D or 3D. If it is in 2D, you will be doing this. If it is in 3D, you will be doing this.
Right.
So I think we should be okay with this. But this is the length of one straight line, which is this. What we need the sum of these all these straight lines.
ये देखिए लेंथ सर खनाउंदा ये सब हिक जेतरी होंदियो या उन मुख्तलिफ थी सकंदियो या
If you are going to take these all to be equal, that would be very good.
ऐसा लेंथ स्मॉल खण हो जाए ना तो जी
Yes, as small as possible. That's why we apply a limit.
एक्यूरेसी जी भली पैदा
Yes. So what is going to be the arc length of this curve? This arc length is approximated by, I am not writing equal sign. I am just approximating it with these all delta li's, and I am going to take their sum from 1 to n. N would be any fixed value. Okay, it's not going to be infinity right now. So then I'm just putting the value of delta li, which is going to be delta xi square plus delta yi square plus delta zi square. So I claim this is the arc length. The arc length is the approximation of these all delta i's, but I am taking their sum starting from 1, and let's say this is 1, this is 2, this is 3, this is 4, up to this is n. So this is the approximation of the arc length. How can I get better and better result? What should I do?
limit tends to 0.
Yes. So the better approximation would be limit n goes to infinity. It is going to be the better approximation. So why it is going to be something better? Because when you decrease the length of this, when you increase the value of n, what happens? This line would be smaller and smaller and smaller. And in this way you can approximate the actual curve in a very good way. Can I convert this particular thing in integration?
Yes.
Because we know very well, if we have some sum and we are going to apply a limit as n goes to infinity, we can convert this particular thing into integration. So this is the idea how you build the things. Now I am doing one thing. I can convert this one into integration, but I just multiply delta t and divide it. So limit n goes to infinity, sum from 1 to n, and when I take this delta t inside, I can write this one as this, delta xi over delta t whole square. Is it okay? Is it okay up to here?
Yes.
Because when I take this delta t inside this square root, this becomes a square, and when I take it over here, this becomes delta t square, delta t, and delta t square.
Why we have taken this delta t by this change?
Because when you apply some sort of limits, then this particular thing is converted into derivatives. This becomes dx by dt. From delta xi over delta t, this becomes dx over dt, dy over dt, dz over dt. And we claim that for this curve, our generalized equation is, we know very well, x of t is going to be the x component. I can write it as f of t I hat plus g of t j hat plus h of t k hat. So this is my x and this is my y and this one is z. So when you say that when you apply limit, this happens basically the integral from whatever the value of t you are taking in the beginning. Let's say this is a and this value is at b. So this is your integral from a to b, or you can call this one to be t naught up to any fixed t, or from a to b integral. This is dx over dt, or you may also call it f prime t plus g prime plus h prime dt. This is what we call Arclength. So what happens, you have to just memorize this particular thing, but what happens sometimes we forget the things, but we can build the things in a good way. So this building is basically dependent upon what we call the fundamental ways of calculus. So this is how you find out the arc-length of some particular curve that lies in 2D or 3D from point A to B. So what if this particular curve is 2D? What happens?
So h of t is 0.
Yes, simply. So this is the formula. When h of t is 0, so this particular thing is removed and we have this equation to find out arc-length. So if you take this particular thing, let's say this circle, and we want its arc-length from this point to this point, then what is the parameterization? This h is going to be 0, this f of t is going to be cos t, and g of t is going to be sin t. We just differentiate, put these here, square and take a square root, and take the integral from some points, let's say a to b. This is going to be what we call the arc-length for that particular circle. But I think the parameterization we use basically for circle is in terms of theta. That is r cos theta and r sin theta, and third component is going to be 0. So I think this whole quantity is going to be 1, and then we are integrating from 0 to pi or 0 to 2 pi. We'll get the exact answer what we need. So it's okay. So we can apply this to find out the arc-length of a particular curve.
In your mod form भी लिखी चलिए
In mod
form dt
हाँ सर आया ना
dr
Yes.
upon dt mod
d alpha upon dt mod integration 0 to
Yes.
ये भी है.
So you call this to be alpha, and
Alpha t.
mod
integration dt
and yes, not square or square root. Okay. So in this way, r of t and mod is means the length of this vector, and length is defined in this way, dt. That's all. But I emphasize this particular thing, otherwise I would have written the exact formula. Okay, this is the
So भी
formula.
आया सर radical 1 plus dx by dt dash whole square dt ये भी आया सर कुछ.
Yes, it is there.
वो drive मुंडो है ना माइट करो.
Same thing, same thing. What you do here, if I am going to remove this, then this becomes a 2D curve. Okay. Now what you do, this is f prime of t, this is g prime of t. You divide f prime of t with both of these. I am just giving you a rough sketch. Then this becomes
F
1
1
and g prime of t over f prime of t. In some other sense, this becomes dy by dx. So the formula for the arc length in I think 2D is this one as well. 1 plus dy by dx.
whole square.
This is when you are not using any type of parameterization, but this is when you are using some sort of
This
parameterization.
is the fundamental
Yes,
formula. So these can be derived from here.
yes, yes, yes. These all can be derived from here easily. So this is what you use for arc length. Let us go ahead.
अच्छा ये ट्रांसफर 2D ला 3D ला बत्ते जो लिखा
in 2D because we have simply dy by dx. To graph the functions in 2D or 3D. You know how to do it in 2D. So 3D graphs and what we call contours. So our main goal now is to construct the graph of a function which lies in 3D. But the question is, how do we do in 2D? I give you any function, let's say, let's take the case of 2D, y is equal to x square. How do you do it?
आराम जरा आसपास था x में पॉइंट्स विजी करे y में कठी करे को ऑर्डर पे उठाए करे वो प्लेन ते ड्रा करे या सैंपल कर्व ड्रा करे सरो भाई पैराबोला करवा.
So our input is x, our output is
f of x.
f of x.
Yes, sir.
So what do? You take the value of x
X.
and you get the value of f of x. What does x represent? X represent any point
Yes, sir.
on this particular line which we call R. And what does this represent?
On y axis.
Or in other words, we may call it the height above that point x. And height always goes in y direction. For example, this particular function is taken as x square. If we put the value of x to be 1, the square of 1 is going to be 1. So I'm taking this point 1, and what does this 1 represent? It represents
One height.
height above this point. It means this length should be equal to 1, or this height should be equal to 1. And if I put here 2, that's going to be 4. So it means here the height is going to be 4. So this height is going to be 4. Then I join these points. Simply I get the graph of this particular function. So here how many inputs do we have? We have one input x, and how many outputs do we have? We have one output, that is y. One input is x, one input, that is f of x or y. What if our function is this? So how many inputs do we have? 2. And how many outputs do we have? 1. So what does this represent?
Space.
Yes, this particular function represents a surface in 3D, a surface. That surface can be a plane, that surface can be some sort of paraboloid or hyperboloid or something like that. So this is a function whose inputs are 2, but the output is a single one. What does this represent? If you just compare this with this idea, you have a plane, what we call it, xy plane. Okay, and in this xy plane, you can represent any point with, let's say, an ordered pair, we call it AB, or in other words, we call it xy. And what does this surface represent? Let's say this is the surface, and above this point xy, we have a point, what we call it f of x comma y. What does this represent? This represents height above the point x comma y. So this is the idea behind that. So you have any point which lies in this xy plane, like you took two values, one for x, one for y, and you put in this function. What you get? You get the value of z. What does it represent? It represents some sort of height above that particular point, and you take these all the heights, you join them, and you get a surface. The surface can be smooth, can be differentiable, can be continuous or not, that's something else, but you always get some sort of surface like that. But it is very much difficult to draw these surfaces. it is very much difficult. Sometimes it is very much difficult to draw graphs in 2D, we know very well. There are some equations which are cubic or quartic. There are some trigonometric equations or exponentials. If you are drawing their graphs, it is again a very hectic task. But again, extending it to 3D is going to be very much difficult. So we have an idea to study these particular things and what we call them to be contours. So, any idea what is that? What's a contour?
वो तो सर ना जो कंटूर इंटीग्रेशन का हल करना है कहीं भी कर्व जी.
No, that's something else. That's something else. There's integral around a curve, I think.
Yes.
What we call line integration or contour integration. But contour integration in complex is, I think, when the curve is closed,
चलो सर.
then we call it contour integration. Otherwise, simply we call it line integral. So, what we do basically, I give you a 3D curve. Let's say that is this. Z is equal to x square plus y square. And you know very well we name this thing particular to be f of x comma y. What type of shape is this? It's a parabola type shape,
3D.
but in 3D. So we take a parabola like this and we rotate it, we get a parabolite like cup or the lower half of egg type shape.
जैसे ये कि मत ये लगन में केबलिंग जो लगन तो सर या छाचे वाले dish सर.
Yes, but that's a bit different. This is simply like this. Yes, it is simply like this. You have this type of shape. But simply it is very much difficult to draw it. What we do, we take a particular height. Let's say this height is z is equal to 1, this height is z is equal to 2 and 3 and 4 and 5, and we take a particular piece from this curve over here and we project it down on the xy plane.
यानी सर्कल सुना
Yes.
साइज बदलने की वजह हाइट
Yes.
होना.
We slice this, we cut this, we get a circle and we are going to project it down on the xy plane. Then what we get? We get a circle here basically. Then we take this particular and draw a circle on this xy plane. We take this particular one and draw a circle on xy plane. And these circles in this xy plane are called contours. Each and every circle is called contour or contour path, and this whole graph is called contour plot. So this idea is again a bit difficult. You look at this, you make the graph, you project it down, very much difficult. We are doing something else. Just look at this thing now. This is f of x comma y, and we are going to make it equal to a particular constant. Let's name it c. Then this particular thing, what we call f of x comma y equals c, becomes x square plus y square equals c. What does this equation represent? X square plus y square equals c. Family of circles whose center is at origin with different radii. When you change the value of c, you can put the value of c to be 0, 0 is a point, then 1, 2, 3, 4, 5 and so on. So what you do, you just get this particular thing, f of x comma y equals c. And what is this c? C is replaced on behalf of z. What does this z represent? It represents height. So what does this c represent? Again represents height. So each and every contour represents a height, but all the graphs lie in 2D. They represent height on this, but they lie in 2D. We call this equation to be the family of circles, But each and every equation like this represents a contour for this particular function. And why these are important, it will be clear in next few minutes.
तो सर
Yes?
सर ही जेड़े भी सर किस्म जी इक्वेशन 3D जी खणंदा से उन में जेको तरीक़ा कार आहे वो इहो ई थींदो सर उन जो डाउनवर्ड शेप खणंदो वरी वो अपवर्ड वेंदो
Yes.
माना it is based it means it is a common thing.
It is a common thing. It is a common thing. It is not necessary it is downwards and it is expanding. It might be expanded, then it comes down. It is not necessary because it depends upon shape.
Upon a function.
The shape that you have, or the function that you have. You might see these things in these figures that I am going to share with you. Okay, so I think you have better idea about when you have a 3D curve and you are going to find the contours for that particular graph, and you have a practical example related to mountains as well, because this is applied in topographic maps, because whenever we are going to study the geographical aspects of a particular area, then we always see that where the height is maximum and where the height is minimum. So we have these ideas which are applied in that case as well. It will be clear in next a few minutes that why we need these things, why these things are so much important. Okay, any question about this?
लेवल कब से कब जाहिर में लेवल कब आसान मुझे एक
These independent curves
और लेवल कब
are level curves, are contours, are contour paths, but the whole graph is called contour plot. The whole graph, because these shows the level, these shows the level independently. So I am taking an example in 2D case. I have these contours. Let's say one is this. Do you have an idea about these graphs?
So 1 upon x minus plus.
1 upon x and plus and minus.
And then we, if we repeat its value, then we maybe find these graphs separately.
Separately. It means you claim it to be y equal
Plus 1 and 1 upon x.
plus minus 1 upon x. Okay. Is there any other idea behind that? Basically, these are contour plots or level curves for this particular family of curves. X square minus y square equals some constant c. And when you extend this particular thing to 3D, then this becomes simply, you remove this, you get this particular surface. Can you tell me what type of surface do we have for this? When we go in 3D and we are going to draw a surface like this, that becomes a shape what we call hyperbolite. Like some saddle shape.
Like rectangle hyperbolite.
Rectangular hyperbolite. Some saddle type shape. You have something downwards here, then upwards in this direction. What we call it saddle. So this is a study which you can do easily. And this thing is very much good when you go for some sort of animations. Then it will help you to understand these ideas. Otherwise, using board to explain these things would be a bit difficult.